Okay, thanks a lot, Alex. So I will take in a very different direction. I will look into another very important feature in the cold forest landscape. My work focuses on lakes. We'll still stick with carbon cycling, but now we're looking into the aquatic environment. And I will give you an example. I looked into the importance of the connectivity between the terrestrial and the aquatic environment. And the data that I will show is focusing on one particular environmental stressor, and that was acid deposition, and how that might have changed carbon cycling between the terrestrial and the aquatic environment, and particularly looking into the role of lakes as an important part of the terrestrial carbon cycling as a carbon sink. The work I will present you now is focusing on the Sudbury area in central Ontario, close to the Quebec border. And Sudbury is a prime example, or it's the perfect site to study the negative effects of humanity on the environment. So after the discovery of nickel and copper ores in the Sudbury area during the late 1900s and during the late 1800s, so Sudbury became a major smelting and mining area. By the 1960s, Sudbury was the second largest global point source of sulfur dioxide to the atmosphere. Then the combination of acid deposition, pollution, logging in the area, and fires essentially created a moon-type landscape with all the vegetation was removed, destabilizing soils, increasing soil erosion to lakes, which then led to exactly this beautiful landscape we have down there. But then on the other side, Sudbury is also an example for what we can achieve if we recognize issues and address those and try to actively remedy the damage we've done in the past. And following the decline on the emissions from Sudbury smelters, is shown in the upper left corner, the red line plot, the landscape started to recover, which was enforced by restoration activities. And with this recovery, we also see this recovery in lakes. So this data from 82 lakes in the area. And what we see there is an increase about 1 pH unit from the 1980s to most recently. So a strong chemical recovery of the landscape and the lakes following emissions reductions and the recovery of the landscape. And with this increase in pH, you also have seen a strong increase, actually a 50% increase in dissolved organic carbon, DOC. And dissolved organic carbon is a very important component, or it's very important for the functioning of aquatic systems, as it determines several chemical properties. It affects how productive the systems are, it affects oxygen levels, it affects water quality. More from a practical point, if we have more carbon in the water, we have to remove more carbon before it can be used as a drinking water resource. And then, of course, it's important for the carbon cycling, or the role, essentially what happens to the additional carbon in lakes. Is it going straight to the atmosphere? Is it just transported downstream and it's ending up in the ocean, or is it stored long-term in lake sediments? And this term, and because the increase in dissolved organic carbon is associated with an increase in water color, that's why it's referred to as lake browning or lake brownification. And what we've shown in the past, the previous study, is that what we knew from monitoring data, okay, carbon concentrations are increasing. From monitoring studies, we know, okay, there are several processes that can affect carbon concentrations on lakes, which climate change, nitrogen deposition, increasing productivity in the terrestrial as well as aquatic environment, and as well as acid deposition. What we showed in this study is that we used an inference model that allowed us to reconstruct how the DOC concentration in the water column has changed over time. And what we clearly could show is that with the onset of smelting and mining area, that led to a decline in dissolved organic carbon concentration you shown in the uppermost panel. And the data is expressed as relative change compared to pre-industrial, pre-1850 conditions. So following the onset of acid deposition, we have a strong reduction, about 40 to 50% in lakes across the Sudbury landscape. But then directly following the emissions reductions, we have this shift towards recovery, really emphasizing the importance of acid deposition for the mobility or the solubility of carbon within the soil solution, which then affects how much carbon can be transported from soils to streams and lakes in the end. But it's also important to know that our data showed that while recovery is ongoing, the lakes or the aquatic environment are still not recovered, since we are still below pre-industrial conditions. And the lowermost panel just shows that essentially the trends we're showing essentially mirror changes in sulfur dioxide emission and deposition data, where the gray data is, well, combined data for the US and Canada, but the red line plot is more specifically reflecting the emission data from Sudbury. So with understanding how dissolved organic carbon in the water column has changed over time, the next logical step was to look, okay, what do these changes mean for carbon sequestration in lakes over time? If we have such large changes in dissolved organic carbon in the water column, how is that affecting how much is stored within lakes? And then, of course, also how important are these changes compared to other stresses that affect long-term carbon storage in lakes, like nitrogen deposition or climate change? And what we did in this study, we looked into changes or in carbon accumulation rates in 8 lakes. We focused on 4 lakes that are located within this dashed area, which is this heavily impacted area, essentially where most of the vegetation was destroyed, which allowed us then to look into the chemical effects of acid deposition, as well as the effects related to direct physical disturbance, soil erosion, the loss of vegetation. And then we focused on 4 lakes that are more or further away from the smelters, which allowed us then to more specifically look into only the chemical effects on the mobility of carbon from soils to freshwater without having direct disturbances in the watersheds of these lakes. And just to show how different these 2 types of lakes are, one is high impact and one is lower impact area. I'll just show you some very basic physical sediment properties. So the uppermost panel shows the water content. The second one is the dry bulk density, so how dense the sediment is. And then the lowermost panel shows the mass accumulation rate, so how much material accumulates over time. And what this data for the high impact lakes shows that it's quite complex. Lakes have different dynamics, essentially reflecting the individual disturbance dynamics. If we just focus on the blue lake, baby lake in this case, the strong decline in water content, increase in dry bulk density, it just reflects increased inputs of mineral organic matter following the loss of vegetation and increased soil erosion. And then the low impact lakes essentially see very little change over time. So reflecting that these lakes have essentially not been exposed to many direct human disturbances. And the only changes that we're seeing are essentially linked to the natural development of lake sediments, which is dewatering over time with increased compaction. When we look into how then the actual carbon pool has changed in these 2 systems, the high impact lakes, again on the left, and the uppermost panel again shows the inferred dissolved organic carbon, so how much carbon has been in the water over time and how that has changed. And what we see is essentially that what I presented you earlier from earlier studies, so that following the onset of smelting and mining, increased acid deposition led to declining dissolved organic levels in these lakes. And then with the reduction in emission, we see this recovery process again, so a return to almost pre-industrial conditions. And then the lowermost panel shows actual concentrations of carbon in the sediment, where we see somewhat similar trends, but they're quite variable over time. And in contrast, the low impact lakes are fairly similar in terms of how dissolved organic carbon has changed, which again reflects to the importance of the direct chemical response to changes in soil pH and the ionic strength of the soil solution. But then in contrast, if you just look at the carbon concentration in the system, there's a very little change compared to the high impact lakes, which also indicates that most of the changes that we see in the high impact are likely a function of reduced or increased mineral organic input. So it's rather dilution than a function of a lower DOC load in the water column. And now this is now the actual data I was trying to get at. This is how have carbon accumulation changed over time. And again, we can see high impact lakes, fairly variable, different trends, reflecting the individual trends depending on when the lakes have been disturbed, to what extent have active restoration activities taken place in these environments. And then on the other side, the low impact lakes, where we only see the effects or the chemical effects, show again very little change over time. And when we look into this more at a landscape perspective, you can essentially say that acid deposition has not really caused any long-term changes in these systems. And I could end my talk here, which would be kind of boring, but the interesting fact is that this trend of very little change, or essentially no change in the not directly affected systems, is very different from what has been shown for everywhere else in the northern forest biome. And I compared my Sudbury data here, which is presented in red, to the data presented by the Heathcote et al. In a 2015 papers, where they looked into minimally disturbed, so lakes without a direct human activity within the catchment, across the northern forest biome, mostly lakes from Minnesota. And what they showed that essentially since the mid last century, we had essentially a doubling of carbon accumulation rates in lakes that reflect similar conditions, which is in strong contrast with what our data showed. And Heathcote et al. Assigned or proposed that this strong increase in carbon accumulation over time is a consequence of increased nitrogen deposition. When we look into our lakes, what's interesting, we see the effects of nitrogen deposition as well. Here I'm showing you delta 15N, so nitrogen isotopes, where essentially we see in our lakes an accelerating decline starting in around 1950, which is just reflecting an increased contribution of lighter nitrogen from anthropogenic sources. So similar to what has been shown for other lakes outside of the Sudbury area, we see also the impacts of nitrogen addition, but we don't see, this has not led to any changes in, or not positive changes in carbon accumulation rates in Sudbury, which is interesting. But the question is then, why are our lakes so very different from what has been shown elsewhere? And the answer to this is the amount of acid deposition that Sudbury lakes have received compared to all the other study lakes, all the lakes from the Heathcote et al. Study, where we see in red is the Sudbury data. So Sudbury received at least twice as much acid deposition. This is data from the early model data from the early 1980s. And this contrast is probably even larger, because this is already after Sudbury emissions have been reduced by over 2/3. And what we propose is that without the effects of acid deposition, we would have seen a similar development in the Sudbury landscape, but that acid deposition has potentially suppressed this increasing trend that has been observed elsewhere in Sudbury lakes. And just to summarize, so in the Sudbury area, we have seen little change in carbon accumulation rates. This is in strong contrast that has been shown elsewhere. And the fact that this is likely linked to acid deposition means that once the landscape has fully recovered from the effect from acid deposition, there's a strong potential for further increase in carbon accumulation rates in lakes in Sudbury, but as well also in other areas in Northern Europe, as well as Northeast North America, that have been affected by acid deposition in the past. And that's it. Thank you.
Thanks a lot, Carsten. It added really well to the diversity and complexity of the research presented today. Is there any question for Carsten? Yes. Oh, sorry. Yeah.
Yeah, I got a question for you, Carsten. Do you think you could use the information that you gain from lakes that have a fair amount of acid deposition, use that as a way to basically partition, if you sampled more lakes outside of Sudbury, but a way to partition the influence of nitrogen deposition over a larger area, and also then maybe the vegetation influences from all the mining activity around those?
Yeah, that is exactly the plan. It's work that has been ongoing. For example, in an earlier study, we compared the Sudbury area to, it's called the experimental lakes area in Western Ontario, where we have very little acid deposition. And what we saw there, that we have initially had a small response to acid deposition, but that effects of climate change are the dominant stressor in that part of of the water or in areas that have received little acid deposition. So there are, in fact, the concentrations are about 10% above pre-industrial level at this point. So we are showing that now with the acid deposition becomes less and less important, or we're recovering from this impact. The climate change is now the most important driver of change. And of course, these techniques can be applied to other environmental disturbances like forest fire, to see how much does the loss of vegetation cover or the soil organic carbon pool, how much does that affect carbon cycling in lakes, and how much will that affect the ability of lakes to store carbon long term. So there's lots that can be done, and yeah, especially working along gradients of different environmental stressors is the plan for more future research.
There was another question from me.
Yeah, in what respect do you think that the fact that in Sudbury they have replanted after the pollution compared to area where there were no restoration, like Rouen, you think it could explain the recreation?
So I think that the difference that we see in our data is that the speed of the time of the response, because the overall driver of changes seem to be linked to really the soil chemistry. So essentially, with the onset of acid deposition, you really directly get changes in the DOC or in the carbon dynamics, similar with the reduced deposition rates. So because initially the idea was, okay, we have these areas that have been restored, but we don't really see a different response in these areas compared to other areas that have not been, where we haven't seen any destruction of the vegetation. And what I believe is that we will see this stronger recovery in these areas only when actually the soil carbon pools have recovered, and that will take much longer than what has been, well, it's only been ongoing for 30 years, so that's just a slower process. So far, when I have to be careful when we talk about what are the effects of restoration in our data, because essentially we can't really say there are any effects yet, but that doesn't mean that they wouldn't come in the future.
Okay, thanks.